All right, today we're tackling one of the biggest, most fundamental questions in all of neurobiology. How do you build a brain from scratch? We're going to go right back to the very beginning. We're talking about the first decision an embryonic cell ever makes on its path to becoming part of a nervous system. So, where does this whole incredible journey even start?
I mean, it's a pretty mind-boggling question when you really stop and think about it, right? In the absolute earliest stages of development, we just start out as this simple structure, basically just a collection of cells. So how on earth does this basic little sheet of tissue get the right instructions to form something as ridiculously complex as a human brain and spinal cord?
Well, it turns out the answer lies in one critical initial process, a single command that just sets everything else in motion. It's called neural induction, and this is the absolute non-negotiable first step in building the entire central nervous system.
Okay, the brain's first blueprint. To really get this, we've got to look at the brain's very first architectural plan. And listen, this isn't about connecting neurons just yet, not even close. This is about deciding which cells even get the chance to become neurons in the first place.
So what exactly is neural induction? Well, at its core, it's basically a decision-making process for cells. You see, the early embryo has this layer of cells called the ectoderm. And these cells, they face a fork in the road. They have a choice. They can either become epidermis, skin, or they can become neural tissue, which is the future brain and spinal cord. Neural induction is simply the process that pushes them down that neural path. All right, section 2, the default neural fate. And this is where things get really fascinating and maybe a little counterintuitive. For decades, you had scientists working their tails off trying to find the signal that tells a cell, hey, you, become a neuron. But, as it turns out, they might have been looking at the whole problem backwards.
Yeah, check this out. Ectodermal cells will become neurons if they receive no signals at all. This whole idea is called the default model. And what it suggests is that becoming a neuron is basically the factory setting for these ectoderm cells. If you just leave them alone with zero external signals telling them what to do, their default path is to become neural tissue. I mean, that's a pretty profound idea, right? That at a cellular level, this incredible complexity can arise from the absence of an instruction, not just from getting one. So think about it like this. An ectoderm cell has two choices. Option 1, it gets a block signal and it becomes skin. Simple enough. Option 2, it gets no block signal and it becomes the neural plate, the future brain. So it's not about a go signal for the brain. It's actually all about a stop signal for the skin. You take away that stop signal and the cell just automatically follows its pre-programmed path to becoming a neuron. Okay, so how is this default path actually revealed? It's this really elegant blocking the blocker mechanism. Let's walk through it. Step 1, the default path, as we know, is to become neural. But step 2, there's this inhibitory signal called BMP that actively blocks that from happening. It's like the brakes are on. So, step 3, the embryo's organizer region releases a counter signal. And what does that do? Step 4, it blocks the BMP signal. So you're blocking the blocker. It's a perfect double negative that leads to a positive outcome. The cell is finally free to become a neuron. The brakes are off.
All right, next up, building the progenitor pool. So at this point, the cells have received their orders. They are now officially on Team Brain. But here's the thing. You can't build a brain with just a handful of cells. So the next critical phase is all about creating a massive workforce of neural building blocks. It's time to build the progenitor pool. And the key players here are these amazing cells called radioglia. You really need to know about these guys. They are the primary neural stem cells of the developing central nervous system. I want you to think of them as the progenitors, the absolute founders of pretty much every cell in your brain and spinal cord. Seriously, almost every single neuron and glial cell that you have right now started its life as one of these radioglia. So, this initial phase of construction is all about one thing, getting the numbers up. And it does this through a process called symmetric division. It's exactly what it sounds like. Each radioglia cell divides and creates two totally identical copies of itself. It's basically like a photocopier for stem cells, just churning out more and more of the same thing. The only goal here is expansion.
And the goal here? It's crystal clear. You've got to create a huge workforce of these neural stem cells before you can even think about starting to build the actual brain structures. You have to staff up before the real construction begins. So this is all about rapidly expanding that pool of progenitors to get ready for the massive project ahead. Okay, next section. Asymmetric division, making neurons.
So once that workforce is big enough, the whole strategy changes. It's like the photocopier gets turned off and the actual production line starts up. The process switches from just making more workers to actually making the final products, the neurons and all their support cells. And this is done through a new process called asymmetric division.
Now this is the crucial switch to asymmetric division. It's a total game changer. When a stem cell divides now, it produces two different cells. One is another copy of itself, another radial glia, which is super important for maintaining the factory, right? You keep the stem cell pool going. But the other one is a brand new neuro precursor. And that cell is on a one-way trip to its final specialized form. So what do these neural precursors actually become? Well, they turn into two main things. First, you get immature neurons. These are going to be the brain's main signaling cells. And second, you get glial cells, specifically astrocytes and oligodendrocytes. And you've got to remember, these glial cells are the absolutely essential support staff of the nervous system. If neurons are the rock stars, glia are the roadies, the managers, the sound engineers. They make the whole show possible.
And, this switch in division mode from symmetric to asymmetric, it has this huge effect on the cell population over time. You can actually see it really clearly in the graph at the bottom of this diagram. It really shows you the impact of that change.
So look what happens. As asymmetric division really gets going, the progenitor population, that's the brown line, it peaks and then it starts to shrink. But at the exact same time, the neuron population, the yellow line, it just shoots up. It grows exponentially. It's a perfect visual. The factory itself is slowly getting smaller as the pile of finished products gets bigger and bigger.
Okay, let's hit our final section, setting the stage. So let's just pull back for a second and look at what this whole process has actually accomplished. We've gone all the way from these totally uncommitted ectoderm cells to a massive, growing population of dedicated neuro precursors. The stage is now completely set for the next acts of brain development.
So what are the big takeaways from all this? Let's break it down. Number 1, the nervous system's fate gets decided incredibly early on. Number 2, that default model is a super important concept. Cells are basically programmed to be neural unless someone tells them not to be. And finally, number 3, it all happens in logical phases. You use symmetric division first to build up your pool of stem cells, your factory. Then you switch to asymmetric division to actually generate the brain's neurons and glia, your products.
And what's the end result of this whole process? Well, we have our building materials. We've got a foundational population of immature neurons and glia. They're what we call post-mitotic, which just means their days of dividing are over. They're all just sitting there, ready and waiting for their next set of instructions.
Which, of course, brings us to the next massive question. The factory has produced all the parts, right? But a giant pile of parts isn't a brain. So how do these newborn neurons know where to go in this vast, developing structure? I mean, where are they supposed to end up? And once they get there, how in the world do they know which other cells to connect with to form the circuits that are eventually going to let us think and feel and learn? Well, that is a story for another time.